Now we'll be solving question number 30 from exercise 2 from chapter laws of motion from phase 1. Let's see the question. So, a heavy uniform chain partly lies on a horizontal table, meaning the chain is having the mass. Now, if the coefficient of friction between the chain and the table is given as 0.25, then the maximum fraction of the length of the chain that can hang over the edge of the table is, meaning the chain should not go down. Meaning downward pull should be equals to the upward pull. The upward pull is coming, or upward resistive force is coming because of friction, and the downward pull is coming because of the hanging portion. Okay. Now let's assume the portion which is hanging is x. So the total length is 1. Total length is 1 and the hanging portion length is x. So the remaining here is 1 minus x. So I'm taking the total length as 1, so I'll get the fractional value directly. X is the fraction ultimately in this case. So mass of 1 meter, let's say is m, the full mass, 1 meter mass is m, I'm assuming it. So mass of x meter will be x times of m. And mass of 1 minus x meter will be 1 minus x times of m. So downward force in this case will be coming because of gravitational pull of hanging mass. And the gravitational pull of hanging mass will be equals to mass, which is x times of m, multiplied with g. That's the force which is trying to bring it down. Now let's make the FBD of the wrist portion. If I make the FBD of the wrist portion, the downward pull or FD driving force is x times of mg. Now here 1 minus x times of mg will be downward because the mass of this much portion is this only. So at this end, the pull is coming. This is the mass which will be acting downward, which will be balanced by the normal reaction, and then there will be friction. Now this friction will be depending upon this normal, which is depending upon this mass. So first I solve for this, and using this, I got the tension at this point or driving force at this point. And then I am solving the portion which is resting onto the table. The normal reaction in this particular case will be 1 minus x times of mg. And that will give us the maximum value of friction, which is equals to mu times of n, which is mu times of 1 minus x times of mg. Now for critical condition, meaning when the body is just about to fall. So for critical condition, friction we equate with Fk, keeping the acceleration 0. This is the thing. Whenever friction is there and we are looking for critical condition, minimum value, maximum value, or anything, you make the friction as Fk and acceleration you keep it 0. So under the critical condition, the driving force and the friction may be 0 because the body is not supposed to move. Meaning, mu times of 1 minus x mg will be equals to x times of mg, and mg gets cancelled. The value of mu is given as 0.25, which is 1 by 4. So 1 by 4 times of 1 minus x is equals to x. That gives 1 minus x plus 4x. And that gives x as 1 by 5 or 0.2, or you can say 20%. Meaning 1 by 5th portion of the rod, if it is hanging, then the body will not be. That's the maximum portion which can hang. In that case, the driving force is just equals to the friction as the body is not moving. If it's slightly more than 20%, even 1% is more than 20%, then the driving force will become the more than Fk and the body will start moving. So in this particular case, the value is coming out to %. So how we have solved, like first we solved the hanging portion separately to calculate driving force. And then we went for the portion which is lying onto the table. We solve the condition for just to move. Okay. I hope you understand this concept. Thank you.